Greetings, fellow cosmic travelers. It's your host A here. As we hurtle through space on this pale blue dot, our tireless telescopes and probes are constantly peering into the abyss, sending back postcards from the edge of understanding. Every year the universe throws us a few curveballs, discoveries so strange they make us question the very textbooks we've written. This past year, 2025, has been no exception. In fact, it might be one of the most bewildering years on record for astronomers and astrophysicists alike. We're not just adding footnotes to our knowledge, we're finding entire chapters we didn't even know were missing. So, what happens when the cosmos doesn't play by our rules? What do we do when we find signals that defy explanation? Imagine you're scanning the heavens, listening to the faint hum of the cosmos, when suddenly you pick up a signal. A burst of radio waves, incredibly powerful, lasting only a few milliseconds. We call these fast radio bursts, or FRBs. For a long time we thought most were one-off events, cataclysmic explosions like the collapse of a massive star. Then we found some that repeat, which was a puzzle in itself. But in 2025, we found something that took the mystery to a whole new level. A repeating FRB, yes, but this one had a rhythm. It wasn't just repeating at random intervals. It was periodic. Like a cosmic metronome, it would burst for a few days, go silent for a precise period, and then start up again, right on schedule. A natural phenomenon, billions of light years away, keeping a beat. This wasn't the chaotic signature of a random explosion. It was ordered. This discovery sent shockwaves through the astrophysics community. Our solar system is not an island. Occasionally we get visitors from interstellar space. Comets, asteroids ejected from other star systems. We identify them by their trajectory. Their path is a hyperbola, too fast to be captured. We've spotted a few of these, like the famous Oumuamua and Borisov. In 2025, we detected another such interstellar object. Let's call it Xenon. We scrambled our best telescopes, including the James Webb Space Telescope. We performed spectroscopy to analyze the light and determine chemical composition. We expected it to resemble comets or Borisov, but that's not what we found. The chemical fingerprint was bizarre, unusual isotopes in wildly different ratios. For example, the ratio of oxygen 17, oxygen 18 was completely alien. These ratios are fingerprints of the disk where it formed, radically different chemical evolution. We assume planetary ingredients are set by stellar nucleosynthesis. This challenges that. Unexpected elements could make planets fundamentally different. Imagine a world built from a different set of Lego bricks. This fleeting visitor opened a window on the diversity of planetary systems. Our recipe is just one of many. One of our most powerful tools for studying exoplanets, planets orbiting other stars, is transit spectroscopy. By analyzing that spectrum, we can deduce what gases are present: water vapor, methane, carbon dioxide. It's like reading the ingredients list of a world. This year, a long-term campaign on a nearby hot Jupiter. Instead, they found something confusing. The planet's atmosphere was changing, rapidly. From one observation to the next, the signatures shifted dramatically. Strong water vapor and carbon monoxide. Later muted, while exotic metallic signatures like titanium oxide appeared. It's like watching weather on a world light years away, far beyond Jupiter or Saturn. What could cause planet-wide upheaval so quickly? Colossal storms dredging up deep material. Violent star-planet interactions, periodic CMEs, even volcanic-like activity on a gas giant. This transforms our view from static to dynamic, turbulent, rapidly evolving environments. Mechanism unclear, energy immense, mystery ongoing. In our current understanding, galaxies are built by gravity, primarily dark matter. Dark matter forms a vast halo. Luminous matter falls in to form galaxies. So, galaxies should sit in halos, especially ultra-diffuse galaxies, UDGs, as large as the Milky Way, with 1,000 times fewer stars, almost transparent. In 2025, a detailed study of one such UDG, Erebus, measured star cluster velocities to get total mass. Result: the visible stars account for nearly all the mass. little to no room for dark matter. A galaxy-sized object, seemingly stable, with almost no dark matter halo. Perhaps not a traditional galaxy, maybe a tidal dwarf from stripped gas, leaving dark matter behind. In some circumstances, gravity could separate dark and normal matter. Erebus challenges galaxy formation theory. If one exists, could there be others? Is dark matter not a prerequisite? Or is Erebus a rare exception that proves the rule? This single faint smudge of light forces us to re-evaluate the role of the universe's most mysterious substance in building cosmic structure. The stars seem eternal, but they live and die. A recent sky survey compared images years apart. The older image showed a star. The new image showed nothing. It hadn't exploded. No remnant, no nebula. It just blinked out. Months later, the star had returned, shining as before. A transient stellar disappearance. Mundane idea. An extremely dense, opaque object passed perfectly in front. But what could be that dense and invisible, and aligned so precisely? Failed supernova to black hole explains disappearance, not reappearance. Unknown extreme variability, gravitational lensing snuffing the light. We're so far in uncharted territory that even wild ideas are on the table. This star's game of cosmic peekaboo is a mystery of the highest order. All obvious errors ruled out. The star was there, then wasn't, then was again. For now, we watch and wait. When we think of rings, we think of Saturn, the other gas giants too. The common thread: massive planets have rings. In 2025, a stellar occultation revealed something startling in the outer solar system. Tiny dips before and after the main event, a symmetrical pattern. That is the telltale signature of rings. The object was tiny, a cosmic pebble, yet it has a distinct ring system. We saw this with Chariklo, now again, even smaller and more distant. How can such feeble gravity capture and maintain a ring? Models struggle, perhaps a shattered moonlet or gentle cryovolcanism feeding the ring. Conditions for rings are more common and less restrictive than imagined. It forces us to rethink ring physics and wonder how many tiny ringed worlds await discovery as they pass before distant stars. The outer solar system is more dynamic and complex than we thought. Frozen worlds adorned with delicate halos. The radio sky is full of pulses, pulsars, the atomic clocks of space, and FRBs, powerful, millisecond flashes from distant galaxies. In 2025, new low-frequency telescopes found something strange inside our Milky Way. Much slower than pulsars or FRBs, seconds to minutes, low energy. Aim every telescope, optical, X-ray, high-frequency radio. Result? Nothing. Empty patches of sky that occasionally sigh in low-frequency radio. Long duration implies a large emission region, or a very slow process. Low frequency points to plasma environments. Standard pulsar models fail. Maybe an ultra-long period magnetar dying out, or plasma clouds tangling with the galactic magnetic field, or a free-floating planet's magnetosphere interacting with the interstellar medium. Whatever they are, these slow whispers reveal a new galactic population, and we have no idea what they are. Hard to study. Origin unknown. Clues are few. The hunt begins. The search for life is a search for chemistry. We look for complex organic molecules, the building blocks of life. JWST pointed at a small, frigid moon of an ice giant. Nitrogen freezes solid, methane falls like snow, one of the coldest places. Yet the spectra were unmistakable, complex organic fingerprints embedded in the ice. Not just methane, pHs, and hints of nitrogen-containing compounds, precursors to amino acids. How did they get there? Delivery by comets and micrometeorites, or in situ formation? High-energy radiation could slowly build complex molecules from simple ices. This radically expands the habitable zone for prebiotic chemistry. Heat not required. Countless cold worlds could be cosmic factories. The raw materials for life may be far more widespread than imagined. In the deep freeze, chemistry persists, life's story might begin in places we once overlooked. And there you have it, a whirlwind tour through the cosmic weirdness of 2025. From rhythmic radio bursts that defy our models, to ghost galaxies held together by an unknown force. From stars that vanish to the building blocks of life in the coldest corners of our backyard. Each discovery reminds us how little we truly know. They touch our origins and our place in the cosmos. Every odd planet, every foreign rock, enriches the grand tapestry of existence. Our solar system and our rules of physics may be local variations on an infinite theme. The universe is under no obligation to make sense to us, so let's keep that sense of wonder alive. Keep asking questions, keep challenging assumptions, and keep looking up. Who knows what mind-blowing discoveries next year will bring? Thanks for joining me. Until next time, stay curious.